All right, so first, if you're interested in going over your answers on the test, I'm going to do that in my Monday and Wednesday office hours, today and Wednesday. So when you come in, I will tell you which problems you got wrong specifically, and then we'll go through the test together, okay? That doesn't mean that I'm not there for other questions during office hours as well. So please be using office hours, and please, you don't need like a specific homework question in order to come in. You can even come in and say, I'm confused about this entire idea. Or you can come in and say, I don't know what to do, right? And I'll help you. I'll talk to you. I'll talk to you about the emotional side of class. I'll talk to you about the ideas of class. Just please come, and if you're not free during office hours, make an appointment. What I'm going to do is add one more office hours for the people who have a class during my office hours. So as part of homework for this homework due Wednesday, it's going to be that if you have a class during Monday, Wednesday, 11:45 to 1:15, I'm going to ask you to send you all my free times. I'm going to try to put a third one that fits as many people's free time as possible, okay? All right, the class videos, I finally got them all up to date. I had to redo a bunch of them, but I did summaries or recaps, so please be using them. Yesterday's is, not yesterday, but Friday's is also there. And finally, if you don't have a laptop, but you want to use your iPhone or your iPad, GC is now available for that. So if you want to, just send me an email and I'll get you, I don't know if you can use the same code or not. Try that code, and if it doesn't work, email me and I'll get you a different code, okay? Do not pay for it. Part of this class is that we're coming up with the money to pay for your GC license. All right, so let's begin by talking a little bit about how we're going to change now that we're talking about non-constant rates of change. So we're going to change a little bit how we talk about dx and dy. Now remember, up until now, we've only been talking about situations that have a constant rate of change. And so we said dx is the change in x, dy is the change in y, right? So we're almost going to keep to that same thing. The only difference is now, we're only going to talk about dx. The second we start talking about dx and dy, you're going to say, oh, we're talking about a constant rate of change. It's always going to be a constant rate of change. The reason is we can't do anything with varying rates of change. Like, we have no idea how to deal with them. And we're going to say now dx is only a tiny change in x. Because if it's a constant rate of change, you can use dx as large as you want. But it's when the rate starts varying, like when the velocity starts speeding up and slowing down, now we can only pretend it's constant for a tiny little amount of time. So dx is now going to be a tiny, tiny little change in x. If you ask the question, how tiny? Well, you're just going to say, we're deliberately going to be vague about that, because what we're going to do at the very end of this unit is just take dx and make it smaller and smaller and smaller to fit our needs. Okay? So don't worry about how tiny it is right now. Just think it's a teeny little bit of change in x. dy then has to be a constant multiple of dx, right? Because as soon as I start talking about dx and dy, we're all going to assume we're talking about a constant rate of change. And it's going to be a constant multiple of dx. And if you notice, I didn't write down a meaning for dy. And so that's what we're going to come up with today. And again, remember, now that I have all the technology up to date, I can upload this about maybe an hour after class ends, and so you will be able to watch this again. So let's briefly talk about a moment and a constant rate of change at a moment using our example. So you can be looking on your laptop, or you can be looking on with the person next to you. And this is the question that I gave you for homework. So you kind of do have to move it to the side a little bit. So I said I went driving directly south of my house for 6 minutes. I drove away for 4 minutes, and then I drove back for 2 minutes. And this is a record of how south I was from my home at every single moment in time. And we want to figure out what my velocity is on the left. Now, last time on Friday when I tried to do this, one person said, can I use a derivative? Well, I don't want you to use the idea of like taking the little exponent, bringing it down in front. If this doesn't mean anything to you, then it doesn't matter. But do you have ideas about what derivative means? Then absolutely use that, right? Use your meanings. So I'm going to give you guys about 3 or 4 more minutes, and I want you to figure out what goes right there in that question mark. Okay? You can use the graph. You can use all your meanings for what does it mean to have a rate of change? How can I find out exactly how fast I was going at 2 minutes? So talk to each other, and remember, always think about not just how do I answer the question, but how can I answer the question meaningfully? Ooh, that's important. Get a real good estimate. So why there? I'd like to yeah, so this is divided by time. You know, the better way is to find the slope between 2 points that are very close to there and figure that out. Yeah. So then that would be what like miles per minute. 0.1 because what's the last velocity increases? Yeah, no, that's fine.
I have a jacket. I have.
No, but like the one you got from college. Oh, okay.
I don't have that.
She told us to use. Yeah.
If you want risk. Plus, so you take someone down with you.
Yeah. Yeah, and I got him at last. I didn't say anything.
Especially on
No, but like just being on top.
What is your idea?
So it's lost.
And so what's the number that you got? 1.25. And now, when you're looking at velocity, if you're putting a number there, that's going to be a percentage, right? What's the last word? But didn't you use the totals? Right, use this total distance. And his total. Can you change that around? To be involved in that change. So it's nice.
So it would be the slow. Oh, are you going there? Yeah, cool.
All right. Oh, can I get this? What is this? Documents. All right, so let's look back up here. So we need to be really clear about what we're looking at, and I saw a lot of people talking about how to find this. So I wanted to ask this group right here, because what I saw a lot of people doing as a learning experience, so that's good. Honestly, sometimes if you do something the wrong way and then you see the right way, it sticks in your head more than if you just did it the right way. So everyone, give yourself a little pat on the back. No matter how you did it. Oh good, everyone's listening to me, good. All right, so I saw a lot of people doing this, and I'm gonna come to you guys in a second, but first I wanna ask the other tables, you found the values here, and you found that at 2 minutes, he had gone 0.23, is it? 0.23 miles, or 0.25 miles. And so a lot of people did 0.25 divided by 2. Can anyone put into words why you can't do that? Who can put into words why that actually does not give you his speed at that moment? Yes, wrestlers.
It's because you're looking at the overall total change. So what you need to do is you need to calculate the slope very close to that point so that you get the specific slope for that specific time.
Perfect. So when you use this, what you're saying is how at this time, let's look at how many miles he went. When you divide them, by the way, what you actually get is an average rate of change, and we're not going to worry too much about that idea right now. It's actually kind of a hard idea for people to wrap their minds around. But you're looking at his average speed or velocity from the time he started all the way to there, right? Because you took 2 as the total minutes, but isn't 2 also the change from here to there, right? And so now you're looking at this giant interval of time when we just really want to look at that moment. Because we had several people absent on Friday. Can someone else tell me what would be a moment at time t equals 2? Anybody? I forgot to look this up. Can someone give me a moment? Yes, sorry.
2.0009.
That will give me the length of the moment. Can you instead name the moment by telling me where it begins and where it ends? No, just like, what's the beginning of the moment? What's the beginning value? The 1.9999, right? And then 2.11. When you subtract it, you're not saying the noun, the object. You're saying the measure of the object, right? All right, so what you can do is, I think on a Mac you have to hold down Shift. Is that it? Yes. And if you draw a little box around there, you can go zoom in. And so everyone right now, if you have your laptop, what I want you to do is keep zooming in until it looks, well, how long do you think I do need to zoom in? Do you think, whoa, no, that's not what I meant at all. Stop. Okay. Do you think that if I zoom in like this is good enough to estimate the constant rate of change? Why? What about it gives you a hint that it's not good enough? It's still curved, right? Now, this is definitely a moment at x equals 2, all right? If I go from, can't read it really well, I apologize, 1.5 to 2.5, that's definitely a moment at x equals 2 because it contains x equals 2, but it's not good enough to give us a constant rate of change. But if I go ahead and zoom in again, and maybe even zoom in one more time, all right. So right now what we have is where it is essentially linear. And this is actually a big deal for us. Okay? We're going to talk a lot about finding a moment where the function is essentially linear. Sorry about my handwriting. All right, essentially linear. Let me make that L look less like two I's in a row. Okay, so once we find that, we're going to call that either a linear or a Kroc moment for a constant rate of change moment. Okay, so there are moments, and they can be any size, but a linear or Kroc moment has to be where the function is essentially linear. Now I can use this information to find a constant rate of change at that moment that's pretty darn exact. And so let's go maybe from 1.999, there we go. So at 1.999 minutes, I have gone 0.2354, that's good enough. And then if I move over to, whoa, nope, wrong thing. If I move over to can I get to 2.1 exactly? If I go to 2.001, I'm at 0.23615 miles south of my home. Now, we're not talking about the entire span of time for the first 2 minutes. We're just talking about that tiny little moment. Again, a moment's not a single point in time. It's a tiny little interval of time. During that tiny little interval of time, right around 2 minutes, I can find my speed or my velocity. So can you guys now go ahead and calculate what is my velocity at that point and fill in the question mark. You can either write in the parentheses, or you can write from and write two blanks.
Okay.
Sorry. So it's going to be from here to here. 2.001, oops, or and there's two ways that you can write the moment, the linear moment, right? There are all kinds of moments, but you want to get a tiny little one that's linear. And notice how much you have to zoom in depends on how kind of wonky the function is, right? If the function's got really mild curves, then you're not going to have to zoom in very much to get a linear moment. But if it's incredibly going up and down like that, then you're going to have to zoom in even more. What do you guys get now for the change, right? So again, And see, this is where I want to mention, someone wrote this, or someone said this out loud, that velocity is distance over time. And I know that you've been told that, but it's not actually true, is it? How can we rewrite that? How can I change that? Yeah. It should always have those d's or at least those deltas in front of it. Velocity is change in distance over change in time. And so what do you get for the velocity at t equals 2 minutes or x equals 2 minutes? Anybody? Yeah, I heard you say it out loud. What is it?
0.375.
0.375. All right, so then what can I do with that? Where does that information go in our file?
Your water value for like the velocity.
There you go. 0.375, right? All right, so I'm going to now clear everything. And I'm going to zoom back out so we can look at the whole thing. No, that's not it. And so how did we get just this one point in the velocity graph is by looking at a tiny little interval, right? We can never look at the one point, and that's really important. We have this idea that this dot at x equals 2 for velocity corresponds to this dot at x equals 2 for position. But do you see how that can't be? If I only have one dot, I can't calculate any changes. So it's kind of a complicated idea that each of these dots represent a tiny little interval over here, not one dot over here. You okay?
Sorry.
No, you're okay. All right. So now what I want to ask you guys is, so imagine now if we did have the entire graph up here, which I'll get to later, probably only by tomorrow. Every single point of there would come from an interval there. Almost those intervals overlapping, right? Because if you think about, not that there's really a next point, but if you think about the idea of the next point is going to come from an interval, and that interval is going to kind of overlap the first interval. Because there's no other way to get two intervals for 2 points next to each other. So it is kind of a complex idea. Now what I want to talk about is what we can use this 0.375 to do. So what I want you to do is this. Keep your function up. On paper, nope, you guys found 0.375. On paper, I want you to write an equation that gives a really good estimate of the distance from 2 minutes to 2.1 minutes. So I want you to fill in what goes here. Okay? Just from 2 minutes to 2.1 minutes, just a tiny little bit over. How can you use that constant rate of change to predict how far I went at every point? 2.0, 2.01, 2.02, all the way to 2.1. Okay, good.
So what if you do instead of with the slopes would be the same?
It would be different. It would be a worse estimate. And so the idea is that to get the idea, for us to learn the idea, we just need to get a really good estimate. And then you want to talk about, well, what would give you the best estimate? So what would be the best estimate? So if you kind of zoomed in forever, not that you actually could, but it's like going, the more you zoom in, the better your estimate gets.
Oh, okay, thank you.
All right, what goes in that blank? Predict what is the distance south of home for all the moments in time from 2 minutes to 2.1 minutes. Tell me exactly what this is. Show the information. So we're pretending it stays at a constant rate of change of 0.375 miles per minute, just for that little instant of time. Oh, sorry, we do know. So someone asked, can Can we use the y at 2? Absolutely. What is, oops, nope, go back. When x is 2, what's y? What is the distance south of home? How can you get that? It's on the graph to the right, right? And so what is it? It's 0.23. Yeah, there we go, 0.236. Or actually, let's make it completely precise. Can someone tell me all the decimals that it gives you?
2, 3, 5, 7, 8, 8.
Okay, so you do have this information. You have this information. Oops, didn't need to do that. And you have this information, and saying if we pretend it keeps at that constant rate of change. You're using your own understanding of what it means to move at a constant rate of change. You're on the right track. Finish it up now. Because constant rate of change times 3x times 1. Because it's not true that y equals mx.
But if it's still
Reasons have changes, guys. This problem could be done with totals. It's taking a lot more time than if you did it with the changes. X is always changing, so can you always figure out how much decreased from when you use some information? So, words like that really have to put it like UILP. Use it this way because it helps to like think about it. Now, what you did is found how much you did at x equals. Can you do it every x change value of y using your same strategy? The idea that you're only doing it for 2.1, can you do it for every value from 2 to 2.1? For every value to 2.1.
The delta x.
So now you have to replace the change in x's. What is the change in x? At 2.01, 2.01 was the change in x.
So,
And what about 2.1 was the change in x? And what about 2.08 was the change in x? And what about at any point? No, because you're trying to, you're adding the time, but we're trying to get overall distance. So, you have to write it down. Just tell me, abstract the right thing. When I gave you the time, how did you figure out the changes? You do x minus 2. And so what about the time x? Right? And if that's your time to change x, then what's the time to find y? And if that's your time to change y, what's your new y? Does anyone have any ones? Pretty much, you just need but what's the dance?
I know.
So, guys, you do it at any moment. Any moment at x equals 2.01. What's the change in x? 0.01. What about at 2.1? What's the change in x? And what about at 2.05? What's the change in x? 0.05. All right. What about the change? What about at time x? What's the change in x? And what's the process that you always do? When I give you a number, you know what to do. So when I at 2.08, how did you change this? What did you do with it? 2 minus my number? 2 minus 2.08? Oh, sorry. So what if I say the number x? Time x. X is going to go between 2 and 2.1. X minus 2, I just want to explain that with a tiny little change in x. Okay? And it's going to increase all the way from nothing to 0.1, isn't it? As x goes from 2 to 2.1, dx goes from nothing to 0.1. No, only at the end. Only at the end. At every point in time, it's x minus 2. If that's your change in x, what's your change in y? Good. All right. I'm having lots of people get it, so let's go ahead. So we want to imagine 1, 2, 3. All right, here's my x-axis. I'm having x go from x equals 2 to x equals 2.1, right? Pretend like you can read that as 2.1. All right. In which case, what is dx going from, guys? What is dx at this point? If x is still at 2, what's my change in x from 2? Nothing. And what about when we go to the end of this little interval I asked you to talk about? What's dx going to? And how do we describe that? If I give you x, how can you figure out the little dx, the little change from t equals 2 minutes? Anybody? X minus 2. All right? Here is now my little dx. How does that help us? Well, now we can predict. Again, it's not going to be an exact estimation because the rate, as soon as we go from 2 to 2.0001, my velocity changed, right? But we're pretending just for a moment that it's staying at this rate. Then how can we predict how much did my car move forward just in that little change in time? In this little change in time, how much did my car move forward or backwards? Times 0.375. Perfect. All right. This is now the tiny little change in distance that I am predicting that I went. But that's not how far I am south of my house, remember? The quantity always has a specific meaning, south of my house. That's not how far south I went of my house. That's how much further souther I went of my house. So how can I get how much I really am south of my house? Oh, Whitney.
Plus 0.23578.
Perfect. 0.2357888. Everyone, we're going to put this into our document. I want you to do it along with me. But because we're writing on the second graph, you need to put little apostrophes, okay? Apostrophes on the y and on the x, and over here on the x. It's not a mathematical thing. It's a programming thing. Just to say, hey, don't put this on the velocity graph. Put it on the right graph. So if you are looking on, then please be thinking about how you would do this on your own. And if not, everyone, put your cursor right after our point. Press Control Enter. And let's write y prime equal, no, not capital, y prime equals. So if I do x prime minus 2, that's my change in x. Highlight it, put it in parentheses, times 0.375, that's how much it'll change, plus 0.235788, is that it? 5788, comma, from 2 to x prime to 2.1, and hit enter. And don't make that yellow because you can't see yellow. Let's make it red. Okay, so just type exactly this. The prime is apostrophe, so it's right underneath the quotation marks.
Wait, so why is the point?
If because when we went to this graph and we found out that y change right around x equals 2 and we divided the change in y by the change in x, we got 0.20.
I know, I was always wondering for having.
It is. And so now look what happens. If you put, let's put x equals 2. If you put 2 in here, 2 minus 2 is 0 times this is 0, and you do get that, right? Now, when you hit enter, do you see anything?
No.
But it is actually there. Where do we need to go to look for it? The apostrophe? All right, so I'm going to go over here. I'm going to hold down shift. I think maybe Windows people don't need to hold down shift. I can't remember. I'm going to draw a little box around 2.
For Windows,
You do? Okay. And look. Do you see it? Once you get right around... Move over. It does a pretty darn good job of estimating, doesn't it? It's a little off. At the beginning, it's perfect. At 2, it's perfect. And then as x increases, because we didn't keep the true rate, but we decided to pretend it stayed at a constant rate, the estimate starts to get just a little off. But do you see how we're still essentially getting the right rate? But what if I tried to do this all the way to x equals 3 or 4? Would it still be essentially the same? It starts to get way off, right? And so what's happening is, look at these little change in x's and changes in y. Oops, hold on. Let me get to the beginning of this. There we go. Oh, this is because you guys had a more precise value than I did. All right. And so look what's happening. As x increases from 2, 0.375 allows us to estimate how much the y is changing. I'm going to turn off the equation we did just for a second so you can see what's happening. At the beginning, our estimate's perfect, and then our estimate starts to get a little off, right? But if we keep our intervals small enough, using a constant rate of change is still going to give us something that's essentially good enough. If I get a distance that's to the nearest 0.0001 mile, then that's going to be good enough. And let's say maybe it isn't good enough. Maybe it's some sort of car crash and I need to have something down to the nearest inch. Well, then I just need to use a smaller interval, right? How accurate you want it to be says how far you can go away from where you calculated the rate of change and still be like, oh, this is good enough. If you're kind of casual about it, you can go further. If you're really, really strict about it, you can only go a little. But we can predict what happens in the future based on the constant rate of change right here. That's the only way we can do it if I stock my information. If I did this, I'm going to stop this at 2. Okay? So, let's say that we have a situation where I had all the information about my distance up until 2 minutes, and then I lost it. But the only way you can go forward is to use the constant rate of change right there and go forward. All right, so what we've talked about today is, and we still have a little time left, so we're going to do something else, but we did talk about how we can take a tiny little change in x, calculate a tiny little change in y using a constant rate of change. Can you put into words now what that dy is? That's my question for you to talk about for a minute. That dy. So that dy in my picture is, actually I won't say, I'll ask you guys. Let me just make it only go forward. If dx is a tiny little change in x, then according to what we did today, what does dy stand for? Go, take a minute, and then I'm going to call on someone to ask. Why? All right. All right, everyone. Right now, I have a change of 0.09. So what is my x? If my dx is 0.09, what's my time? If my change in x is 0.09, what's my actual time right now on my stopwatch? What's the time right now? So where do we start? We started at 2 minutes, right? And now how much did I change? 0.09, so my time is now 2.09. So I'm right here at 2.09, okay? And there's a gap here, right? So I have two distances that I need to think about. One is my distance of this vertical line, and the other is if I move my finger up a little to right here. Which one of these is dy? The longer one or the shorter one? The shorter one. Because didn't we say that we're always going to use dy as a constant multiple of dx, right? This is 0.375 times the dx. So is dy now the change in y? It isn't. This is the change in y, right? I'm going to write it up there so that, because if you're rewatching the video, that does not make any sense. So right here, this is the change in y. Sorry, this is dy, and this is the true change in y. This is the true change in distance. So then, if dy is no longer representing the true change in distance, then what can we call it? How do we get it? Use the situation. Use the story about me driving. What does dy now represent? It can't be the change in distance because the change in distance is actually a little bit more. This is my true change in distance. So what does this represent? This one's the change in x. Now, I thought people were contributing. Keep going. Change in time same as change in x, right? So here's my change in x. Here's my dx. Here's my dy. So think about why this isn't the same. How did we get this? How we got this is not what it is, but it can give you hints as to what it is. In a real world example, if we measured this, and someone said, "Oh, is that actually how far you went in that 0.09 seconds?" You'd say, "No, but it is." It is an estimate that we used by doing what? What do we do in order to get that estimate? There's an assumption we made. There you go. This is how much we predicted I would move by making an assumption that I would stay at a constant rate of change of 0.375. Okay? So now dy is not going to represent the real change in x. It's going to represent the estimate of how much the y changes based on having a constant rate of change. And what happens if I take a truly, truly tiny little change in x? Then what happens to my estimate? Look at the difference between the bar and the line. What happens to my estimate? It becomes essentially accurate, right? All right, so moments, rate of change at moments. What could dx and the dy mean? You only have like 1 or 2 homework problems, and I will see you, because I want to make them due tomorrow. All right, let me ask you this. Would you prefer a small assignment due tomorrow and a small assignment due Wednesday, or just like a longer one due Wednesday?
Wait, are you gonna post it today?
I will post it today, and I'll make it due Wednesday. It's not going to be longer than the 2 added together, okay?
Oh, yeah.
All right, I'll make it due Wednesday. Everyone, if you have time right now, come talk to me and let's go over your test.
Could you also say dy is a tiny change in y when there's a tiny change in x?
You only have to change it to the estimated change in y.
Oh, okay.
The tiny estimated change in y when there's a tiny change in x, assuming a constant rate of change.
Okay. Thank you.
Whenever you receive your test back, just so that I know which questions I got
I
wrong.
can't hand them back because we use them over and over. That's why if you come to office hours, I'll tell you right now which ones you got wrong and we can go over.
Okay, perfect.
Okay? Hey.
Is it possible to check which ones I got wrong?
Yeah, can you come to office hours now and I'll tell you exactly which ones you got wrong, and then we can go over them. I'm sorry? In my office, in like 10 minutes.
Okay.
Okay?
What place? What room?
308. But if a lot of people come, I might change to a different room on the same hallway, but I'll put a sign up.
Can I make an appointment to go over my test?
Yeah.
Awesome.
No. Actually, give me just 1 second to write this down. Estimated change in y due to assuming a constant rate of change from x equals 2 to x equals 2.009. Yeah. Okay, now I can stop it.